Well, it's different again. It's about what are called multivariate functions. And the stuff that we're doing in chapter 14 is where Calc 4 begins. So when you come to do Calc 4, hopefully some of you at least will do it, you're going to be dealing with multivariate functions for the entire course. So it's got a nice theme again. What you're going to do, or what we're going to do, is the intro. What are they? How do you find limits of them? How do you sketch them? How do you differentiate them? That's kind of what we've got. So it would be a bit like 141 and 151, right? So how do you sketch them? What do they look like? What are their limits, right? And finally, how do you calculate? Well, let's show you what a multivariate function looks like. This is a multivariate function. And it can also be written like that. That's the equivalent in 141 world of things like y equals x squared and f of x equals 2x squared, right? So in a multivariate function, there are two or more variables. Well, for the most part, we're going to deal with two independent variables and one dependent variable, right? So technically in math, when we did this in 141, x was the independent variable and y was called the dependent variable. So what do these things look like? Well, we've seen a little taster of them. Remember the equation of a plane, right, that kind of thing? If you rearrange the equation of a plane, let's say I had a plane that was 2x plus 3y minus z equals 10, right? Imagine that was a plane. If I rearranged that, you could get z equals 2x plus 3y minus 10. You see, that would be a plane. That would be a multivariate function, right? Any given x and y, there's a different value for z. So let's show you. Our first thing is, how do you sketch them? And I'll show you that in a thing called GeoBra. After how you sketch them, we're going to look at evaluating them, finding their values. After that, I think we're going to go for their limits. That might be actually a little bit ahead of the game. Let me just, yeah. And then after that, we'll go into the next section. So first things first, let's see. I'm just getting some windows here. My brain is all over the place today, so you're just going to have to hang in there with me for a little while. Okay, here we go. We have a function or a piece of software that's online called GeoBra, right? We've used it before, right? For if you want to see the equation of a plane, for instance. And here are some really pretty functions that are multivariate. The top function is z equals x squared plus y squared. And it happens to be this fella here. See that little, it's a bit like a cup that goes up forever. And if you rotate it, it's got a lot of symmetry to it. You see it from above, it's a circle. From below, well, the green one gets in the way, but you can see it's pretty interesting shape, right? And that has the equation that the z value, which is essentially the vertical height, right, is equal to x plus y, right, squared. And the green one, x squared plus y squared plus z squared equals 4. Wouldn't that make you think of a sphere, right, which is basically a three-dimensional circle? Kind of cool. Now, I'm randomly going to try and break it now. How about z equals the sine of x, y? And let's see if I can click these guys off. There we go. Now, would you look at that for a very, very interesting 3D surface? that the height, Z, is the sine of the X and the Y coordinates. So X and Y is the floor, right? So if you pick any point on the floor, right, it'll have a 3,2 and a 5, pi, whatever it is. If you find the sine of those two things multiplied, you get the height. And what you've got here is a very, I mean, just look at the symmetry going on there. I mean, depends on the orientation, but can you see waves like crests and dips, crests and dips? Can you see that you could model a very basic wave system in 3D by simply just having a formula that looked like that? So these are very, very useful things. In the real world, in the world that most engineers live in and physicists live in, would you agree it's 3D, not 2D? Right? We've already done the space curve, right? We know that things fly in 3D. That's one example of 3D. But functions and surfaces, and whatever you want to call them, they're very important in 3D as well. Okay. So if you want to see what something looks like, go to GeoBra and type in the equation, like Z equals X squared plus Y squared, or X squared plus Y squared plus Z squared equals 4, or any of the ones that I've got down here. And with a bit of luck, GeoBra will know what the heck you're talking about and draw it. So that's sketching. You can have as much or as little fun as you want on sketching. It is not a big topic. You know you're not going to get really anything in your final on that, except maybe X squared plus Y squared one, because then I'd expect you to know it was a sphere, but that would be very minor, and it would be a multiple choice if I even wanted to do it. So let's look about how do you calculate the value of a multivariate function. Right, that's more realistic. I'm trying to open the right window, but for the life of me, I can't seem to find it. And found it, yay. Okay, so let's take an example of a multivariate function written in this format, which is quite useful. And it was X plus Y over X squared plus Y squared. Dead easy, it really is. Don't overthink this. If someone asked you, what is the value of the function 1, 2, X would be 1, Y would be 2, wouldn't you simply just do 1 plus 2, 1 squared plus 2 squared? The top is 3, the bottom is 5, and the answer is 3/5. That makes sense? Evaluate a function. If they make life weird for you, and they say, what would f of x comma x look like? Now think substitution. The first guy is x, and the second guy is y. So x plus y would become x plus x, and on the bottom it would be x squared plus x squared. Are you happy about substituting the second guy, the y, with an x, right? Really, and then you tidy it up, and then you do style points. So far, so good. And you could get f of, I don't know, x plus h, x take away h, right? Can you do that? In this case, you would get first guy plus second guy. So that guy plus that guy. And then you would have that guy squared plus that guy squared. And if you put them together, you end up with 2x because the h's cancel. And if you took this guy, you would have an x squared, a 2xh, and an h squared. And this one, you would have an x squared minus a 2xh plus an h squared. And so you'd have a 2x on the top, and you'd have a 2x squared plus 2h squared on the bottom. And then you could probably take out a 2, and that would be your simplified answer. So you really, oh, my screen seems to be in a weird position today. Yeah. So you end up with a as simple an answer as you can. Are we good with that? Right, so if I say evaluate a function, that means replace the x by whatever this is and replace the y by whatever that is, even if the x and the y are themselves expressions of some kind. Let's look at the domain of a multivariate function. There's an example of a function. If you want to find the domain of a function, it gets changed just a little bit. It becomes the usable values of x comma y. Would you agree that if you're talking about a domain, it's the usable values of x and the usable values of y? And very often domains are given in terms of what they can't be. What is the only combination of x and y that would cause a problem with that fraction?
1, 1.
Well, that's one example of it, but more general than just 1, 1. You're correct. 1, 1 is
the same number.
Right. If x and y are equal to each other, agreed? Right. So how would you write the domain down? Well, the domain would be written if we use set builder notation, which is actually the only real sensible way of tackling this, is you write the set of all points x, y, then you put a vertical line, which means such that, and then you just say that. Or that. What is she doing? Oh, she's okay, she's got an empty bottle, that's fine. Right. Comfortable with that? How about this fella? What would be the problem here? Or you could phrase it, what must be true? Maybe that's a better way to phrase it. What must, say about again, please?
Y must be less than x.
Oh, I think you did too much algebra there. But you're right, y does need to, but the problem is that y could be negative and negative 10 would be bad news. So you're in the right track, you're darn close to being right. Would you agree that the thing inside has to be greater than or equal to 0? So in this case, I'm doing it from the positive. Now, could you say that y is less than x? That's half true. The reason why I can't do what you just said is, can you imagine that x was 1 and y was negative 10? Would you agree that y is less than x? But what happens when you square it? Yeah, ain't any good. So whatever is inside the square root greater than or equals to 0. So you either tell me by what shouldn't happen or in terms of what must happen.
Could you also put the absolute value of x is greater than the absolute value of y? Would that be okay?
That would work. That would be equivalent. Now, how about this fella? I know he's not a two-dimensional function, but we can still use this idea. I wish I hadn't to write all this stuff down. Okay, it's a log function. What must be true? So we're doing it in the sense of what must happen. What must be true about a log function? What must be true about what's inside a log function? That's a better way of saying it. What number must be inside a log function to be calculatable?
Would it be greater than or equal to 1?
Definitely in the right place. Not quite where it needs to be. It only needs to be greater than 0. If you just sketch a normal log function, don't they look like that? Don't they have a problem at 0? That's why it's greater than 0. So basically that. Now, if they ask you to sketch what that looks like, you could go over to GeoBra and just type that guy in, and then just look at what would the shape look like. And I believe it's part of a sphere or something. Not sure. I'm wrong. What is it part of? No idea. Plug it in GeoBra and figure out what the shape is. And there's 4 pictures to pick from. None of them look particularly sphere-like, so we're good. Right. Let me show you a homework question. What you have up here, I hope you can see it, but sometimes it can be weird. Let me make this bigger. Let's try and make it a little bit bigger. Okay. Right. Oh. Whoa, that's big. Right. If you take right down here, this guy here, right? You put it into GeoBra and you look at it, and it's a picture that looks like that, or it's a picture that's kind of more curved like, or it looks like that, right? You see there's basically 5 pictures, and once you find the one that looks like it, you pick it, right? So that's how they get you to do the what does the graph look like question. Right? If I scroll a little bit up, contour maps, don't want them yet. I think, is it up here? Yeah. If they ask you to find the domain of a function, do you see it looks like that? That's the one we just did. And this is the guy you put into GeoBra, and it will look like one of these funny shapes. That's the one that you'll pick, right? So that's kind of where we are right now. We're now going to look at a thing called the contour map. This is going to be a lot easier than it might seem, especially the way I'm going to do it. I'm not intending to do it badly, but suppose you had a function called that, right? Another version of how to write that would be this guy. There is a way to describe or to show what this graph looks like on 2D paper, and it's called a contour map. And a contour map, for anybody who's ever read maps, don't contours look like that, right? You ever seen them, contour maps? All points of equal height are joined together, right? And so that's a contour map. If you ever go hiking or something, you might have a map that's a contour map. It allows you to understand. So when I look at this, do you see a hill that's got 2 peaks to it, right? It goes up and it goes down twice, right? So if I was looking at that, I'd say, oh, look, there's a hill with 2 pretty symmetric looking peaks. I know where I am, right? So how do you use that concept in sketching these? Well, what you do is Z is essentially the height. So you start off with x squared plus y squared equals z. You kind of write it that way around. And then you choose heights. So I'm going to choose a height of 0, a height of 1, a height of 2, a height of 3, and so on, right? And then on your 2D paper, and this is probably the only time in my life I'm ever going to do this with you by hand, because there's some really nice software that does it for us. But if you do z equals 0 here, so there's going to be a lot of rubbing out here. What does all the points that have the property x squared plus y squared equals 0 look like? They end up looking like the origin, a single dot. And then you make the height 1. Well, what do all the points with x squared plus y squared equals 1 look like? Don't they look like a circle radius 1? And then you do a height of 2. Well, what does that look like? Well, that looks like a circle whose radius is square root of 2, which is about here. And then you do the next one, which is the square root of 3. Then you do the next one, and it's a square root of 4. And can you see why I don't want to do this anymore? But what you are looking at is called a contour map. Isn't it kind of like the surface was on the earth and somebody did a map of it, right? A contour map of it. If you were doing it by hand, which thank goodness you're not going to do it typically by hand, can't you simply just do what I just did, but much more neatly? And then if you're looking at that, you have got to visualize that you're starting at the bottom and it's going to curve up the way, and won't each slice be a circle? So I would say, based on that contour map, wouldn't this function, z equals x squared plus y squared, wouldn't it look like a kind of, I don't know, a monk's hat turned upside down, getting bigger forever? An acorn that just was huge, right? Whatever you want to imagine, that's what it would look like. So we want to figure out, is there a nicer way than me doing this by hand? And the answer is yes, there is. And as soon as I open the window, I'll try and show you. Okay, I'll bring this one over here and let's show you the software that should do this. Right. Can you see a guy here called Contour Maps? Fingers crossed, when I click this, you'll be able to see the contour map. There is a contour map. You see, they do it for you. So what do you do here? Suppose I wanted to do x squared. Plus y squared. And see that guy that they're calling A? You could think of him as being Z. I'm going to try if I can call it Z and not screw the thing up. Yay, okay. I don't know why they called it A. I would have called it Z anyway from start. Can you see you've got your contour map? Probably not as nice as mine. Okay, it is nicer than mine, right? But you can do a contour map for anybody. So if I stick a negative in here, can you see how different the contour map now looks? Is that kind of cool? I've got a bit of software to draw it for you. Contour maps are probably a little bit less important than they used to be. Can you imagine when there wasn't nice software? If you wanted to draw a 3D shape, right, a surface, would you agree making a contour map would at least give you some idea of what it looked like? Give you a kind of visual impression. They are still used today because they have other uses than to help you draw it, because we get software that will draw it now, right? So you don't really need a contour map to draw the surface, right? But it is important for other things unconnected with drawing. So that's why it's still here. Okay, would you agree this is a lot easier than it looked when I started? because you're just going to go to software, right? But I just wanted to show you what the software was doing so you get an idea of, okay, I kind of know what it's doing to get those numbers. Move this out of the way. Not even sure where we are right now. We're on my white screen, good. Let's do a question, or at least a couple of questions from the homework, because they're kind of interesting. Two contour maps are shown. One of these is a cone, right? You imagine a 3D cone. Now, cones can go down the way, they can go up the way, right? Orientation is hard to tell unless they put numbers on these contours. The other is for a function whose graph is a paraboloid. Now, a paraboloid is the fancy name they gave to that thing that I couldn't think of what it was, the acorn one, right? The unturned hat, right? Now, there is a difference between a cone and a paraboloid. When you cut a cone at height 1, height 2, height 3, height 4, the circles are evenly spaced. You know, so radius 2, radius 3, radius 4. When you do a paraboloid, they are not equally spaced. They are circles, but did you notice in that really bad one, the circles got closer to each other the further away I went, right? Like it went 1, then it was about 1.4, 1.7 to 2.1, right? It would grow very slowly. So when you look at it, can you see how this one is equally distant? And this one, they are getting closer. I know it might not be obvious, but I can see it. Can you agree they're different? So one of these is a paraboloid and the other is a cone, and you pick which is which, and that would be the answer to that one. Here is a piece of a map, essentially. The good news is that they're telling you the heights, which is great. And on this map, you're given a day and a depth, and the number of the contour is the temperature. Ah, okay. So it's not a physical map, it's representing some. So if I do day 220, which is here, and I move up to depth 10, would you agree that I'm probably on the line that says 12? And so 12 degrees. Kind of works. Well, here is a guy. It says draw a contour map. And there are 4 guys. Wouldn't you go to that piece of software, type that guy in, and one of these would be the guy you would, I think it was this one, wasn't it? Yeah. So you'd pick that one, if it was. I'm pretty sure it was. Plug that guy in. And just pick the picture. Now, this guy, can't you put that into the other software and choose whichever one of the Ripley ones it ends up being? So you're simply just going to put in functions and check out what surface they've got, or put in a function and check what kind of contour map, right? It's kind of match the contour to the function, match the surface to the function. The hardest one of these is if I just give you a surface and I give you a contour map, can you match one with the other? Okay, that would be fun. If I shrink this to the point where you'll actually see it, you won't be able to read the darn things anymore, but you can't win for losing. Okay. If I took this surface A and I sliced it horizontally, a height of 0, a height of 1, a height of 2, a height of 3, one of these guys down here would be its contour map. Okay. So let me pick one that I think is easy to do. E. You see E with all the little bumps? If you cut it at 0, cut it at 1, cut it at 2, which one of these pictures do you think you would get if you sliced up E? I agree. That one, right? Now, once you've got a contour map used up with a graph, pick the easy shapes first. so that when you've only got a couple left, there's only a couple to pick from, right? Let's see if I can pick another easy one. If I pick F, if you imagine slicing F at height of 0, height of 1, height of 2, height of 3, won't you get lots of parallel lines? And they'll all be pointing, for want of a better way, northwesty, right? There is such a thing as northwesty, although I better be careful with the orientation. So I'm looking, oh, there. Oh, of course, the orientation has changed because you know X comes out of the paper. Go figure. So it would be the straight line guy, so I would pick that one. And that is the end of that section. Anything you want me to talk about, apart from that last question, which is basically, you know, look at the thing and pick it, look at the thing and pick it. Anything you want to talk about, are we good? So now we're going to look at our next section. And our next section is 14.2. And that's limits and continuity. There's only 10 questions, so this is a pretty small topic. There are two techniques that we use for finding limits. There are others, but these are the two I'm going to focus on right now. One is evaluate, right? That's basically just plug in the number if you get an answer. Brute force would technically be an evaluate. You know, the ones where you put in infinities and see what kind of answers you get, those kind of things, right? And factor and cancel would be that. So if someone gave you, for instance, in question 1, a limit, it would look like this with a multivariate function. It would be the limit as the xy tends to the number 5, 3, and then they'd give you whatever the expression happens to be. In this case, x squared y cubed, take away 9y squared. Don't overthink these limits. If you can plug in x is 5 and y is 3 and get an answer, won't that be the limit? Right. You know, somebody went and said to you, what is the limit as x tends to 4 of x squared minus 1? Wouldn't you just say, well, 4 squared take away 1 is 15, the answer's 15. I know that's a way back in Calc 1, and then you'll probably ever see just one of them because they're too easy, right? Well, in this case, wouldn't the answer be 5 squared times 3 cubed, take away 9 times 3 squared? And ... because I don't know what the answer is and I'm too lazy to find out. So your first job will be to plug in a number, and if you get an answer, you're done. And that'll actually get you by the first 2 questions. But sometimes, is this going to be one of them? Let me check. 1, 2, and 3 are okay. This one. But sometimes, question 4 is an example of the sometimes, that doesn't always work. Can you trust me if I plug 3, 3 in here, I get the dreaded 0/0 problem. Okay. We don't like 0/0, agreed? Because that means indeterminate form, and that's bad news. So I'm going to use version technique, whatever you want to call it, number 2. I'm going to try factor and cancel. Okay, look at the top term, x squared y cubed, take away x cubed y squared. There are some common factors there. Do you want to tell me what the best common factor you can pull out of both?
X squared, y squared.
Y squared.
Great. And if you do that, you're left with a y take away x. Great. Now, can you do anything about x squared minus y squared? Can you factor it?
It's a difference of 2 squares.
So how about an x plus y, x minus y? So factor and cancel method, you factor and you should be able to cancel. And yes, you can. You might not think it, but think again. X minus y is allowed to cancel y minus x. What gets left behind?
Negative.
-1.
Yeah, -1. So our answer now becomes the limit as xy tends to 3, 3 of negative x squared y squared over x plus y. So that's negative 3 squared times another 3 squared over 3 plus 3. So that's negative 81 over 6, which I believe gets you negative 27 over 2. Are you happy about factor and cancel technique? And that gets you by question 4.
I do have a question though.
Yes.
So
Yes.
basically for the y minus x, that could be rephrased as negative x plus y. So why wouldn't that cancel out the x plus y instead of the x minus y?
If I picked you up correctly, you said, could an x minus y be called
The top one being like y minus
Oh.
x, if you like flip, like rephrased it, it would be negative x plus y.
But negative x plus y isn't the same as plus x plus y. That's why you can't cancel.
I was just thinking in the sense that you're mentioning that a negative would be left over. Okay, got it. I understood.
Right. Let me just show you what was happening there. Right, we had these two guys. I could pull out a -1 as a common factor. Now, if I did that, I'd get negative x plus y. And then I would rearrange this guy here to be a y minus x. Can you see that when you cancel now the -1? That's kind of what's happening. We just short circuit the whole thing, because if you see it enough times, you just say, yeah, you're allowed to cancel, but remember it makes the answer negative. That's the reason it's negative. So that's kind of connected to your idea of switching them around, but
Okay,
this way works.
Okay, now I understand. Thank you so much.
You're welcome. So we have problems. What happens when that doesn't work? And what happens when that doesn't work? Well, in Math 151, didn't you have the conjugate method? You know, with square roots? And didn't you have L'Hopital? So you're hoping right now, aren't you, that I am going to show you a conjugate method or a L'Hopital method, aren't you? But I'm not, because those methods don't work in multivariate functions. Because you need a single variable function to do L'Hopital. And technically, conjugate method would work, except none of the questions are square roots, so we won't show you that because you're not going to see it. But we do have problems that do happen. So how do you deal with it? And it is, it is pretty messy. Let's phrase it that way. It's going to be, I don't know why I'm putting 3 here, except it's the third method. There's a video example on question. Yeah, questions. Let's tell you which ones. 7 is going to look like this. Actually, so is 6. Going backwards here. Yeah, I'm going backwards, so is 5. 5, 6, 7, yep. What about 8? No, Okay, so questions 5, 6, and 7 are going to have this problem where we're trying to find a limit, typically at a point like 0, 0 of a fraction. And so here's one of the examples. There are a number of different approaches to this. I'm looking at their guy, and that's fine. I don't mind what they're doing here. It's not the way I would choose to do it. It would work. Let me hold off on question 6, which is this one. See if I can find one where I can show you the other method. Right, well, 5 is a video, so if you watch the video, they'll actually tell you how you do it, so I won't focus on that one. 6 is I want you to leave for a minute. Maybe they give me one, I'll get a chance on. Yeah, I like this one. I'm going to choose 7. So here is the limit as x, y tends to the origin, 0, 0. And the guy you've got is 8x squared. Take away that guy on the top, and you've got x squared plus y squared on the bottom. And we're being asked to find if the limit exists or if it doesn't exist. And if it does exist, what do you get? Now, if you put, where the heck am I? I've been talking all this time and I don't know if you've even seen what I've been writing. Okay, so here is question 7, right, in all its glory. And if you put x is 0 and y equals 0, you have a big problem. Don't you get 0 over 0? Brute force doesn't work. There is very little factoring that you could do, and even if you did it, it wouldn't help you. So factoring cancels out the window. So I'm now going to do this. Make x equal 0. Just pick it out of there. I'm going to make x 0 because I want to. And I am now going to take this question, and it now becomes the limit as y tends to 0 of nothing, take away 5y squared, nothing over y squared. And, oh, wait a minute, doesn't the answer get you -5? Great. If you make y 0, the answer would be -5. Great. Now, you make the other one 0. And now we're going to be looking at what's the limit as x tends to 0. Well, 8x squared take away nothing over x squared add nothing. And the answer is 8. Now, since both of them are heading towards 0, can't one of them kind of reach 0 first, which is essentially what I'm doing here. But when one of them reaches 0, the answer is -5. And when the other one reaches 0, the answer is 8. When that happens, the conclusion is that the limit does not exist. Does that make sense? You can't be two numbers at the same time, right? If there's going to be a limit, it's a bit like the left limit is -5 and the right limit is 8. Yeah, it's kind of that kind of analogy, right? When that happened, didn't you say the DNE, right? The overall limit does not exist. Are we cool with that? Now, suppose this was 8 and that was 8. Wouldn't you then say the limit was 8? Right? If they were both the same number, you could make a reasonable assumption. Now, they have done essentially what I've said. They've just done it in their own weird way, but that's fine. That's fine. I can handle that. Now, question 6 is going to be done a little bit differently. And they do have a video, but let me just show you how it works. We're going to find the limit as x, y tends to 0, 0. And the function is 6x y squared over 7x squared plus y to the 4th. And this one is tricky I am not going to make x equals 0 and then make y equals 0. If I did that, I would just get an awful lot of 0 over zeros everywhere, and I wouldn't really be any better off. So I'm going to do this. I am going to, which way did they go? They go the x's. Now, I'm going to make y equal mx, which means that as long as I make the limit as x tends to 0, won't y also go to 0? So isn't that a very weird way of just saying both of them go 0? I'm going to make x go to 0, and I'm going to make y m times x. So y is m times 0, so y is going to 0. Now what does that do? Well, you've got 6x y squared over 7x squared plus mx to the 4. And now I'm going to try and find out what the limit as x tends to 0 of this would be. It's going to be 6m squared x cubed over 7x squared plus m to the 4 x to the 4. So far, so good. Right. Replace the y by mx. Multiply it out and combine it best way you can. Is there anything you can take out as a common factor on the bottom that might help us? Anything?
Squared.
Okay. Now, if you take out an x squared, you got that. If you cancel it with that, you're now going to get the limit as x tends to 0 of 6m squared x over 7 plus m to the 4 x squared. Still good? Now, what does that become? Well, when x tends to 0, won't you get 6 lots of m squared times nothing is nothing? And won't you get 7 plus m to the 4 times nothing, which is just nothing? And isn't nothing over the 7 nothing? Right? So if I go that direction, I get 0. And you might think, oh, that's great, the limit is 0. Hold your horses. I just chose that direction. Couldn't I have made y equals mx squared? In fact, couldn't I have made y just x squared? If you do that one, you find out that the limit, because I don't have time, gets you a different number. So the limit is it does not exist. Thank goodness there's only 3 of those and I've done 2. So good luck on the 3rd one. If you are doing the ones, they do show you a video. So at least I'll take you through some of the bits I skip by. And last name, and that is us for today. And that's not bad. We have done 1 3/4 sections in a day. Hopefully not too fast. So I'll hang about for questions. Otherwise, bye-bye till tomorrow.
Professor,
Yes,
I had a question on number 2 of 14.1.
14.1.2 coming up. Ah, shooting space, I shut it up. Wait a minute now. Give me a second. 14.2, question 1.
2.
2, question 2. And okay, so the one is the limit. Okay, I'll show you because it's probably easier if you tell me what the problem is when it's in front of us. So, okay, it's this guy up the top here, right?
No, 14.1, question 2.
Okay, no problem.
And I'm stuck on part B.
Find the domain of f. Okay, so the function that you are dealing with is z take away x squared plus y squared in the square root, right?
Yes.
So I'm looking for usable values of x, y, and z essentially. So I'll set it up kind of the standard way, right? That guy there. We don't need that bit, evidently, as far as WebAssign is concerned. It's good enough just to say the restriction. I don't care what Z is. Z can be anything you like, right? It could be any value. I do have a problem with these two guys. Don't they two guys have to be greater than or equal to 0? And the reason is things inside square roots have to be positive.
I think for the problem, there's a log sign in the very beginning.
Oh, then because there is a log in front of it, the only well then that is a little bit tricky, because what I want is I need this guy to be greater than 0, right? But I also need this guy to be greater than 0. So I need two things to be true. This has to be greater than 0 to make the square root work, and the whole package has to be greater than 0 to make the log guy work. And they went and rewrote this like that. And now I know why. X squared plus y squared has to be greater than 0. Agreed?
Mhm.
But isn't x squared plus y squared guaranteed to be greater than 0?
Yes.
So I don't really care about that because it's going to happen anyway. On the other hand, doesn't this still have to be true? They've just written it that way. I'm hoping that it accepts that. So you don't need to curly bracket, but they're only wanting you to fill in, you know, the piece that would go there. In our case, it would be that one.
I have a question about that.
Uh-huh.
How do you know that the x squared plus y squared is going to be greater than 0?
Well, I know that x squared is positive because anything squared is positive. I know that y squared is positive because anything squared is positive. I know if you add two things that are positive, they're bound to be positive. So I just use logic.
Oh, okay. And then the z minus root of 0 would just be z. Okay, that makes sense.
Right. So that's the only restriction you need to worry about. That has to be true because inside logs, the rule is that the thing must be greater than 0. It's not allowed to equal 0 because it's a vertical asymptote there, right? For logs. And so that has to be greater than 0, which becomes this. But I'm pretty sure if you type that in, it would be equally correct. It would say yes.
It worked. Yeah, it worked.
Right.